participants. Okay, so welcome again. Just proceed with this topic from this morning. And this topic was the signal space. Okay, so, and now I need to go this direction. Ist die Maus jetzt schon? Sind wir da? So nach rechts. Okay, so it's here. And we said, okay, we can represent the signals, let's say 4 signals, by means of a weighting of orthonormal waveforms. And these waveforms, these orthonormal waveforms, basically correspond to the unit vectors which you know from the Euclidean vector space. So, and these orthonormal basis functions need to have 2 basic characteristics. Yeah? There need to be 2 different basis functions, need to be orthogonal. So this means this inner product needs to disappear for j not equal to k, so for 2 different basis functions. If you take a look at one and the same basis function, the basis function needs to have an energy of 1. So this is integral from 0 to capital T, Cj squared of t dt, always assuming real valued signals. So and now, once we have these basis functions, we can proceed and can say the coefficients. Again, a different computer. Insert, draw. Yeah, that's good. The coefficients. No, that's too small. Draw. This. So, okay. Hope this works. The coefficients. Coefficients. Sij, which you see here, yeah, I signal j's basis function, yeah, are given as the following inner products. So we have usually we have to calculate them. Are given as the following inner products. Inner products. So they need to be calculated. Yeah, Sij is equal to, now we measure how similar is our ith signal, which needs to or which should be represented by a linear combination of these basis functions with the jth basis function. So this is the ith signal. Maybe I write it again in this notation where I say I use 2 different colors. A green color for the ith signal. Yeah, this is signal number I. So let's say I of t. Yeah, and then here in red, S, C, J. Okay. S. Okay. S of t times C. It's a different computer. Again, the lecture hall is closed. So this is red J. Yeah, and here we have this green I of t dt. So we need to calculate these in order to have the coefficients. And now we can say, in conjunction with our basis functions, with our basis functions, you know, Cj of t, yeah, we can fully describe our signals Si of t as signal vectors. And for signal vectors, again, I just need to increase the thickness here. As signal vectors, Si, and if I use handwritten letters, I indicate a vector by means of this underline here. If you take a look at, if I write, for instance, the test in the exam, I use boldface letters, yeah, bold letters for vectors. So in the exam, bold letters are vectors, and here I use this underline, yeah, to say this is a vector, yeah, and the vector consists exactly of our coefficients which are required for this linear combination of the basis functions. So here we have, for instance, Si1, Si2 for the highest signal vector, Si3, and so on. And the last one is Sin. If we use capital N of these basis functions, and we usually use in the opposite to information theory encoding, column vectors. Therefore, to save space, I write here a line vector, a row vector, but I use here this T, which means transposed. And now we can discuss the old example. Let's say old example. Now we think we want to find basis functions for a minimum dimension of this signal space. This is our goal, yeah? A minimum dimension of this signal space, and we want to find C or the basis functions, let's say, functions Cj of t, but we want to ensure a minimum n, where n, this n is the dimension of the signal space, is the dimension of the signal space. Now look, we go here to the old examples. These are our 4 signals. And it's clear that it's not enough to use just one basis function, because if this basis function, for instance, is the same as the first signal, yeah, the second signal is just a weighted first signal, that's clear. But the third signal cannot represent it just by a scaling of the first signal. So we need 2 basis functions here. And the main characteristic is they need to be orthogonal. So we could start, and this is done on the slide, we could basically start with this first signal, and this first signal just describes the shape of our first basis function. Yeah, and then since S1 of t and S3 of t are orthogonal, we could use as the shape of S3 for the second basis function, but we don't need more because S2 of t is minus S1 of t, and S4 of t is just minus S3 of t. But I choose here a different version, and you immediately see this works. Yeah, but there are different possibilities for these basis functions. So I say I start with the first basis function, and this is this one. And then I draw a second basis function. Trinity, nur das Menü frage ich. Draw. This is this one. So now we just write here. So here is t, and this is, let's say, C1 of t. And here we want to find a second basis function. And you see, if I define a first basis function, for instance, by a rectangular pulse with a duration of t by 2, this is capital T, this is the shape of the first basis function. And you see the first signal, can be built by means of this, of a weighting of this function, but also the third, the fourth, and the second. And then I can say, I can easily find an orthogonal function, which looks like this. This is orthogonal to the first one. Of course, also the negative version of this is orthogonal to the first one. And this extends from t by 2 to t. And these two signals are for sure orthogonal because they don't overlap. So we see immediately that psi1 of t times psi2 of t is equal to 0. If we integrate from 0 to capital T. So they are orthogonal. But this is not the whole story. Now we want to ensure that these two basis functions are unit energy. So this means if we integrate them over the time and square them, the squared versions are integrated over the time, the result should be 1. So if we would write here 1, for instance, as the amplitude, let's say I write here 1, just 1 as this value, then the integral would be 2 by t. But the integral over the square, so we want to ensure Cj squared of t dt is equal to 1. This is the other characteristic, j equal 1 or 2. And then you immediately see if I write 2 by t square root, and if I square this value here, I get 2 by t if I square it. And then I integrate over a time t by 2, and then the energy is 1. So this is the required energy weighting. We need an energy weighting which ensures an unit energy basis functions. And this is solved by writing here for these examples square root of 2 by t. By the way, if you take a look at the slides, I use different basis functions, but the basic properties between the signals, for instance, the signal energies or the so-called Euclidean distances, are independent on our chosen basis functions. We can use different basis functions, but the characteristics in physics, physical laws in physics, do not depend on the coordinate system. For instance, if we rotate the coordinate system or if we shift it, the laws remain the same. And here it's the same. We can choose even other basis functions. And now the question is, how do we have to weight our signals in order to obtain our original signals? So, and this is by means of this inner product. So we need to calculate S, 1, 1, and this coefficient which describes the first component of the first signal vector is just this integral. So S1 of t times psi1 of t dt. What comes out is quite easy because our signal is u0, and we multiply this by square root of 2 by t, and then we integrate over a time. If we multiply both, then a duration of t by 2 remains. So this means we multiply by t by 2, and what we get is u0 times square root of t by 2. So this is the first component of the first signal vector. And then we write here S1, 2. Now we do the same for the second basis function. So S1 of t times psi2 of t dt. And we get again exactly the same, of course. We get again u0 times square root of t by 2. So now we multiply the first signal with this basis function. So now we can proceed, and it's clear if we take a look at S2, the second signal is just minus the first signal. And since we can represent the first signal as, that's clear, this is our goal. S1 of t can be written now as S11 times psi1 of t plus S12 times psi2 of t. And since we can write this like this, and S2 is just minus S1, yeah, then it's clear that the second signal vector is just minus the first signal vector, yeah, because S2 of t, since S2 of t is just minus S1 of t. This is clear. So we can proceed with S3, yeah, and if we talk about S3, this is also simple, because S3 in the first interval is exactly the same as S1 of t, and our first basis function, yeah, extends from 0 to t by 2. So we can say, okay, our our third signal vector, yeah, how can we describe this? Let's say we just write here the signal vector, yeah. So this means our signal vector S1 consists of the components S1, 1 and S1, 2, and this is given by, now we can write it as you like, yeah. Let's say in this form, U naught square root of 2 by t, U naught square root of 2 by t, and this gives a vector, and we use usually column vectors, therefore we write here this transposed. Yeah, and now what's about S3? If we want to write S3, we can say, okay, for sure, yeah, the first component is again U naught times t by 2, and now we take a look at the second component, but in the second interval, the third signal is just the negative version of the first signal. Yeah, so this means in the second interval, we just become here minus U naught times t by 2. And then it's also clear that S4 is just minus S3 because the fourth signal is just minus the third signal. This is clear. And now we can basically find a geometrical representation of our signals in the signal space, okay? And this is very advantageously, yeah, because we can see basic characteristics of our signals, at least if you have some experience. So we can now, we can find or do a geometric representation of our signals for signals. Yeah? And what we draw is the so-called signal space diagram. Signal space diagram. This is the signal space diagram. And how could we draw the signal space diagram? We just draw one basis function. We draw the second basis function. And since these basis functions are orthogonal, we just represent then later the signal vectors in such a two-dimensional, because we need two basis functions. Yeah? And in this example, of course, since we need two basis functions, the dimension of the signal space is equal to 2. Yeah? So we have two orthogonal basis functions, and these are shown, let's say, C1 of t. Yeah? This corresponds to the horizontal x, and the other one, which is arranged with 90 degrees because it's orthogonal, this is C2 of t. And now we want to represent our signal vectors in this so-called signal space. So how can we do this? Yeah, we just need to draw the corresponding vectors. And then I just use an abbreviation. Yeah, I just define A is equal to U naught times square root of t by 2. Just an abbreviation, yeah, for this U naught times t by 2. T is the modulation or the simple interval. So let's say this is A, yeah, this is A. So then this is minus A. This is also minus A. And then this is A. So the first signal just corresponds to the components U0 times square root by t by 2, so A. So this means the first signal vector points in this direction. This is the geometric representation of S1, when S2 is just antipodal to this S1. Sorry, this is too long. It's this one, right? Yeah, this is just S2 because it has the coordinates minus A and minus A. So the third signal vector has A and minus A. So A and minus A. This is this one, right? This is the third signal vector, S3. And the fourth signal vector, which represents our fourth signal, is this one. So this is S4. And as you can see, yeah, since the first signal is orthogonal to the third signal, and of course also to the fourth signal, yeah, we see in this signal space diagram that S1 and S3 and S1 and S4, yeah, are arranged or basically drawn or rotated by 90 degrees. This means S1 and S3 are orthogonal and S1 and S4 are orthogonal. And S1 and S2 are just antipodal. They point just in the opposite direction, as well as S3 and S4 are antipodal. Yeah, and now we just draw very basic characteristics which can be seen from the signal space diagram. And this characteristic is denoted as the minimum Euclidean distance. And this is the minimum, so the lowest Euclidean distance between the signal vectors. And you see the distance between S1 and S2, yeah, is larger than the Euclidean distance between S1 and S3. I just draw it and later we just define this Euclidean distance. This is not a signal vector. This is just this length of this vector would be d, or of the vector which just points from S1 to S3, for instance. This is denoted as d min, but d min is not a so-called Okay, there was a question in the chat, but it's clear, I guess. Yeah. No. If the duration, we just start with this characteristic that all the signals have a length which is equal to this capital T. Yeah. If they are larger, then you say if they have a larger duration, let's say, then still the time interval where these signals approach zero, yeah, is defined as capital T. Okay, so but it's not restricted. But we simply start with this. Yeah, we assume that our signals are restricted to this interval. Yeah, later we will basically see that this is not required if we talk about modulation schemes. But for the first, this is a simplification which helps us to make the things easier. Yeah, but it's not required. So this is the Euclidean distance, the minimum Euclidean distance. Yeah, and you may have heard about the Hamming distance. Yeah, Hamming distance is the number of different elements between two code words for if you use channel coding. And here it's the Euclidean distance in the signal space. Yeah, this is the Euclidean distance. But not the general Euclidean distance, it's the minimum Euclidean distance. Euclidean distance. And later we will see the minimum Euclidean distance basically defines our bit error probability if the received signals suffer from additive white Gaussian noise. Yeah, and now we can also derive the signal energies, yeah, from the signal vectors, or if you want, from the signal space diagram. Yeah. So next topic, signal energies. So the signal energies are defined as EI. So E stands for energy and I for the I signal. And of course, this is the integral from 0 to capital T because we restricted for the first our attention to these lengths capital T signals. Yeah. So basically, if we talk about modulation, this would be the modulation interval. Yeah. And then we say this is SI squared of T dt. Yeah. But now we represent these signals as a linear combination of the basis functions. So this is SI1 times C1 of t, yeah, plus and so on, Sij times Cj of t, plus, and the last one could be or is Sin, yeah, times Cn of t. We square this dt. And now look, if we simplify this, yeah, we get this expression. This is sum. And now as a sum expression, j goes from 1 to capital M. So n is the dimension of our signal space. It's, of course, Sij to the square. And then times the integral of from 0 to capital T, Cj squared of t dt. Yeah. And this is, of course, because we defined the basis functions to have unit energy. This is just one. And then you may say, but there are remaining terms. There is, for instance, Si1 times C1 of t times Si2 times C2 of t. But the integral from 0 to capital T between S1 and S2 of t and between any pair of basis functions which differ in the index is always 0. So this means we end up in an expression which looks like this. So we can obtain the signal energy just by summing up the coefficient squares of the signal vectors. So this is our signal energy. Maybe we do this like this, yeah, draw. Yeah, we say, okay, this is this. So again, next try, draw this. So yeah, and we say, okay, IE, yeah, our signal energy of the I signal is given by the sum of the coefficient squares of our signals. And if you take a look at the old example, we can see this works, of course, because we can say, for instance, for the first signal, what is the first coefficient square? It's u naught squared times t by 2. And the second one is u naught squared times t by 2. This is the sum of the coefficient squares. So this is, let's say, S11 to the square, and this is S12 to the square. And we end up with u naught squared times t. And this is, of course, the same for all the others. E2, E3, E4, all have the same energy of u naught squared times t. As you can see, they have the same energy because they have the same length. And you can see this is a correct result because in this example, the energy of this signal is u naught squared times t. U naught squared times t. And here, if I square this signal, u naught squared times t. U naught squared times t. So it's the correct signal energy. So this means we can see the signal energy even in the signal space. If you draw this diagram, yeah, of course, we can only draw diagrams for, let's say, 2 dimensions or for 3 dimensions or for 1 dimension, but not for more. Yeah, but still the theory is valid even for higher dimensions. Yeah, but the most important case later for modulation schemes are 2-dimensional modulation schemes with a 2-dimensional signal space, where we only need 2 basis functions. Now we just define the Euclidean distance. Yeah? And once we have this, we can calculate or deal with other examples. Yeah? So now, Euclidean distance, and this is just a definition. Yeah? Euclidean distance. And for those who hear information theory and coding, they know there we use this Hamming distance. Yeah? And this is a very similar property, but here we talk about continuous time signals. And in information theory and coding, we talk about basically code words which are described, yeah, the characteristics by means of a minimum Hamming distance. So Euclidean distance is defined as between two signal vectors, d between, let's say, a signal vector si and a signal vector, let's say, sk. Yeah, this is the Euclidean distance. Of course, I needs to be different from k because we compare two different signal vectors. And the Euclidean distance is just the length of the difference vector. So it's si minus sk or sk minus si. And then we take a look at the norm of this vector. So this is basically, you may also use two vertical lines if you want. So this is the P2 norm of the difference vector. So it's just the length of the vector which connects Si and Sk. Yeah, and of course, if you want to calculate this, yeah, you just need to take a look at the difference vector, and the components of this difference vector are Sij, yeah, minus Skj, and then I square the coefficients, sum them up, and if I take the square root of this, I get the length of this vector. J goes from 1 to capital N. Yeah. So, but usually, if we talk about modulation schemes, yeah, we are basically interested in the minimum Euclidean distance. As for does this mean in order to represent a signal which has a duration greater than t, we need more? So this is the old question. No, we need not more. Sorry, I read it again. I thought it was a new chat. Yeah. So with respect to modulation schemes, not to coding schemes. Yeah. We are mainly interested in the minimum distance. We are interested in the minimum Euclidean distance. In the minimum Euclidean distance. And we write this with d min as in the figure, yeah? D min, and this d min is just the minimum value of all these Euclidean distances. So we take a look at all possible combinations of different vectors and look for the distance between these two vectors and choose the minimum. Yeah, and in the old example, of course, if we write this old example, yeah, old example, you can say, okay, d min is equal to, look, what is it? This is A, this parameter here, this is A, right? So, and then it's 2A, yeah, and 2A is 2 times u naught times square root of t by 2. So this is 2 times A, 2 times u naught times square root of t by 2. This is our Euclidean minimum Euclidean distance in this example. Of course, we can write this differently. We can also write this as u naught times square root of 2t as you want. Yeah. And later, if we talk about the characteristics of the modulation schemes, yeah, we just explain this Euclidean distance as a function of the mean energy between these signals. Yeah. And if we now define just the mean energy between these signals, mean energy, all signals have the same probability, usually, yeah. So this is just the norm. There is also a P1 norm, and this is the P2 norm. Yeah, this is just the length of the vector, which can be drawn from Si to Sk. This means P2 norm. Yeah, you can simply write, if you want, a norm of the difference vector. Yeah, the length is equal to the norm. Okay, there was this question. So just write norm if you want. Yeah, maybe this is okay for you. Yeah, so just write here norm of the difference vector, so the length. Yeah. Okay. So in the mean energy, in this example, it doesn't matter because all the signals have the same energy. Then we would say the mean energy, let's say we denote this as ES, the mean energy is equal to E1 plus E2 plus E3 plus E4 divided by 4, but all have the same value. And these energies were U naught squared times T, right? And now we could say this value here, yeah, can be also expressed as a function of this mean energy. Yeah, we don't need to do this. It's fine. We have the result, but we could do this because we can say, yeah, this is of course also the same as square root of 2, yeah, times u naught times square root of t. And if you compare both expressions, yeah, you see that this, maybe I just put this a little bit lower, yeah. So that this expression is the same. Now, if we want to express this as a function of the energy, you see the square root of the energy, the mean energy of the signals, is just u naught times square root of t. So this would be square root of 2 times square root of ES. Yeah, so we can explain, this is at the moment, this is not so important, but we can explain this Euclidean distance as a function of the mean energy. Okay? Yeah, and this is later really required because we want to increase the Euclidean distance as much as possible in order to be resistant compared to errors caused by noise, by additive white Gaussian noise. But we want to increase this distance for a given mean energy per signal. So this is the goal. So if we want to increase the distance, of course, yeah, we can increase the signal energy. Then the distance increases. But if we have a certain signal energy available, then the question is how can we arrange basically our signal vectors? And just as one comment, yeah, in information theory encoding, you basically increase the Euclidean distance between all the possible signals by means of this coding. So if you say I have a certain code word and I have another code word, yeah, and you would draw the corresponding time continuous signals for a given modulation scheme, yeah, corresponding to these code words, yeah, then you would obtain a signal space with a huge dimension depending on the length of your code words for a block code, yeah, and you basically increase your Euclidean distance by means of the Hamming distance. Yeah, but here we only take a look at the modulation schemes. So now, yeah, we can discuss examples. And for the next section of this chapter, yeah, I just tell you we do this by means of an example, yeah. And if you really need the procedure, take a look at the slides. So 4.2 would be the Gram-Schmidt orthogonalization procedure, orthogonalization diagonalization procedure, yeah, but see slides. This is so simple, yeah, and see examples or seminar tasks. And now we switch to seminar tasks. Seminar tasks, yeah, and you find the new seminar tasks just in the internet, yeah. And now I switch, yeah, to the first task. So now we basically switch to the seminar, yeah. Maybe I do this here. I just give a new name, and this is seminar, whatever. Which number? I don't know. Probably also 9 or so. Yeah, this is a new seminar. Okay. So and now, view draw, view. What's this? Okay, this one. So now draw. So I start with task number 5.1. Yeah, you can take a look at the internet and you find the tasks. And then you see, okay, consider the following 4 energy signals. Now we have 4 signals and we want to obtain a geometric representation of these signals. So a linear combination of the basis functions. We need to find the basis functions and the signal vectors. And then we can also find the minimum Euclidean distance, for instance. Yeah? But this is not asked in this task. So now we can draw the signals. So there are 4 signals, yeah? And the first signal is given as this, as you can see. This is the first signal. So again, I assume this duration, which is not longer than t, if, for instance, t is our modulation interval. And then you see, yeah, there is the signals only change in this interval t by 3. So let's say this is t by 3. Yeah, this is capital T. And here we have a pulse here in this first interval. So this is just our first signal. Yeah. So this is S1 of t. And here we have U naught. Okay, this is the first signal. Then the second signal, how does it look like? Yeah, we draw a figure again. Here's this second signal. This is T again. Yeah, this could be the modulation interval. Yeah. So, and here I have a second signal. It looks like this. Okay. This is S2 of T. It has the same maximum value U naught. And then there is a third signal. And this signal looks like this. T, again, we have this spacing of t by 3, yeah, but here we have t by 3, this is 2 by 3t, and then the pulse is located here, at this position, this is u naught, and this is S3 of t, and then there is a last signal, and it has a duration which is the same as capital T. So all the signals are different, so we could use them to represent for instance, a 0-0 bit combination, 0-1, 1-0, 1-1. Yeah. Also, this is not the best solution, of course, to do this, yeah, because we have 4 different signals. This is capital T, and now the signal looks like this. So this is our 4th signal, S4 of T. And now it's written in this task, yeah, show that the signals do not build a set of orthogonal functions or orthogonal functions. Yeah, and if all the signals would be pairwise orthogonal, then the inner product between any pair of signals need to disappear. And you see, for instance, if you multiply S1 of t and S2 of t from 0 to capital T, we don't get 0 because, yeah, they are overlapping. So this means this pair of signals is not orthogonal. And this was asked for, yeah, that do not build a set of orthogonal functions. Yeah. And for instance, S1 and S4 are also not orthogonal, but S1 and S3 would be orthogonal. Yeah, but S3 and S2 are again not orthogonal, as well as S3 and S4 are not orthogonal. So this means we cannot use the 4 functions to be 4 basis functions because they are not the same. Yeah, is there any relationship between the length of a code word and the modulation interval? Yeah. I don't know if this is the right time to do this, but you could say, yeah, I delete it later. Yeah, for instance, if you have a code word which is this one, this is a code word now, information theory encoding, 0110. This is one code word, and the other code word it's let's say 01001. There are 2 code words. Okay. And now if we use, for instance, antipodal modulation, this is still a bit to be transmitted, but after encoding. And then we would say, if we use, for instance, only 2 different signals, S1 is a rectangular pulse with positive amplitude, and S2 is a rectangular pulse with negative amplitude. Okay, we only use 2 functions, S1 and S2. We could say if we transmit a 1, we transmit this. Okay, if we transmit a 0, we transmit the second signal. If we transmit a 1, we transmit the first signal. If we transmit a 1, the first signal. If we transmit a 0, the second signal. Yeah, so this would be 1, 0, 1, 1, 0. And this would be then in this other context, yeah, one of a lot of, it depends on the number of code words, you have possible signals, yeah, which you consider after coding. So this is T, yeah, and then this would be your modulation interval, but because your code words have a length of 5, this would be 5 times capital T. Yeah, and then it depends on the number of code words. Yeah? Another code word would be this one, and then you would transmit this signal, of course. Yeah, and this is again 5 times capital T, T, T. Yeah, so this means corresponding or to the original bit, to the encoded bits. Yeah, we only need 2 waveforms, S1 and S2. But after this encoding process, yeah, we have as many different signals as we have different code words. Yeah, and now it depends how many code words you are using. Yeah. And you say usually you have these block codes where you may have, I don't know if this is the notation of Marco Henhofer, where you have, let's say, k information bits in a code word, yeah, and n bits including these parity check bits, and then you would have 2 to the power of k different code words used for modulation, and then you have 2 to the power of k different signals. Yeah, so this would be just the corresponds, but we can take a look at this later, even in information theory encoding. So this relation between modulation, yeah, and coding. So okay, now we have this, and now B, task B, find a set of orthonormal basis functions. Use the Gram-Schmidt orthogonalization procedure. And if you use this Gram-Schmidt orthogonalization procedure, you do the following. You simply say, okay, I start with a basis function, yeah, which has the same shape as the first signal. So we basically say S1 of t, so this is the first step. Let's say step 1, yeah, step 1. We simply say the first signal should be represented just by one basis function, psi1 of t, with the corresponding weighting. So this means if we only use one basis function, the first basis function looks exactly as the first signal. So we can draw it here. This is the first basis function. So this is the time t. Here we have t by 3. This is t. And then this is the shape of the first basis function. because the weighted version of the first basis function should be equal to this first signal. But we need to ensure an energy which is exactly 1. And then I have to write here 3 by t square root. Now the signal has an energy of 1, because if I square this, I get 3 by t times t by 3, and we see this energy as exactly 1. So now we have this weighting. And since the first signal only is a weighted version of the first basis function, we do not need to calculate S11 in a complicated way, because we need just to weight C1 of t and not another basis function in order to obtain S1 of t. And since the amplitude of S1 of t is U naught, we simply have to say then S11 times psi1 of t needs to be a single pulse with amplitude U naught. So I need to multiply here with the reciprocal value of this value, because this times this gives just U naught. And now we found the first basis function. So this was, in my opinion, quite simple. And now we proceed. Yeah. So this means step 2. And now we say, you immediately see, if you take a look at the second signal, we cannot represent the second signal only by the first basis function. This is impossible. So we say, okay, if you see this, yeah, or calculate this, you see, now we proceed and simply write S2 of t is S, sorry, is S21 times C1 of t. And now we just indicate this is known. So we have it already. Yeah, this is known because we know the first basis function. It's here. Yeah, and this can be calculated. Can be calculated. This is quite simple to be calculated. By the way, it's the same coefficient as for the first signal, as you can see, because the second signal in this interval looks exactly the same as the first signal. But this is not enough. We can never build S2 of t only with a weighted version of S1 of t. And this means now the new step is plus S22 times C2 of t. And we need to calculate this. Yeah, this difference needs to be derived or calculated. So in the first step, this is known. We first calculate this, and then the remaining part, yeah, which is required in order to build S2 of t, yeah, can be calculated. And then we ensure, if we ensure this unit energy, we have the second basis function. This is the whole procedure, basically. So we could say, how can we obtain S12? Of course, I say S12 is the same as S11, but I just write this. S11 is equal to integral S2 of t times C1 of t. Yeah, this is the second signal, and this is basically a relation to the first basis function. So dt from 0 to capital T. And what do we obtain? So this is our basis function. I multiply this with this. I get U naught times square root of t by 2, of 3 by 2. And then we integrate over this time. And of course, we get this U naught times t by 3. Exactly the same as this S11. So now we have this. And now we can say, yeah, okay. Therefore, we can say the difference, let's write this like this, S22 times C2 of t. For the first, let's say this is a difference. Yeah. And this, if we weight this difference in order to have unit energy, we have the second basis function. And this difference can now be calculated because it's nothing else than S2 of t, yeah, minus, and the red one is known, S21 times C1 of t. So, and this needs to be done. And then we have a weighted version of the second basis function. Let's do it. And then we can proceed in the same way in order to find all the other required basis functions. Let's say, oh, sorry. So I draw it like this. So here, here. And let's say I draw S2 of t in blue. Okay, so it's t. So, and this is exactly S2 of t. So the blue one, this is, oh, sorry, it's this one, right? This is S2 of t. This is S2 of t. This is t, yeah. And now in the same figure, I could draw S21 times C1 of t. So I weight this basis function by this. And what do I get? I get this. So this here, this red one, this is just S21 times C1 of t. And now if I build the difference between S2 of t and this weighted first basis function, I get this difference. Yeah. So this means what remains if I build the difference, it's this. So this black one is SD of t. And the shape of this signal is exactly our required second basis function. We only need to normalize this in order to ensure an energy of 1. So we could say this is the shape. Again, yeah, we obtain this. Yeah. So here it's the time t. This is t. Okay. This is t by 3. And this will be our second basis function. Yeah. And of course, here we have this amplitude u0, and you just have to think about the following. Which weighting is here required in order to ensure that even C2 of t has an energy of 1? And in this example, of course, this is again because the duration of this pulse is t by 3. This is again square root of 3 by t. And now we found the second basis function. And if we have this, we only need to calculate the weighting, yeah, of this basis function in order to obtain this SD of t, this difference signal. So this is just the weighting S22. So this means S22, yeah, is equal to, of course, you could calculate this by means of this integral, S2 of t times C2 of t dt, because now we have C2 of t. Yeah. But what is it? Yeah. This is SD of t, the amplitude is u0. And how do we have to weight this basis function in order to obtain this u0? It's again u0 times square root of t by 3. And then we have it. So now we basically have the first component of the second signal vector and the second component of the second signal vector representation. Now we proceed, and you see here's the signal S3 of t, and for sure we need a further basis function. And the procedure is again the same. So we say step 3, yeah, step 3. And for step 3, we could say, okay, proceed. S3 of t is equal to, what do we know until now? We know C1 of t, and we can easily find S31 because S31 is equal to integral S3 of t times C1 of t dt. And the question is, how large is it? So this signal times this basis function integrated over the time. What's the result? So if I multiply this with this and integrate over the time, what do we get?
0?
0. Yeah, it's 0. Exactly. So, and then we have already the second basis function. Yeah, this is what we have. And it's the third signal, and we need a new weighting. And this weighting as S32 is equal to this integral S3 of t times C2 of t dt. Yeah, and this is, of course, here's the basis function. We multiply this with this signal, and again we get u naught times square root of 3 by t, and this amplitude is over a length of t by 3. So this is again u naught times t by 3, square root of t by 3. But this is not enough. Yeah, there is something missed. If we weight the first basis function and if we weight the second basis function, we will never get this signal because here this remaining part, yeah, is not contained in psi1 of t and not in psi2 of t. This means now there is the new part, and this is S3 3 times psi3 of t, because we need a new basis function. And again, we could denote this as difference of t, yeah, the difference signal. So how can we obtain the difference signal? Yeah, we just do the same as before. We say, yeah, maybe I draw it here. Therefore, SD of t is just S3 of t minus, and then the known components, yeah, S31 times psi1 of t minus S32 times psi2 of t. Yeah? And then we have the difference. And once we have the difference, we just have to normalize this difference signal in order to have to obtain unit energy. So we draw the next signal, and this signal looks like this. This is S3 of t. This is t. This is t. T by 3. And here u naught, and this is S3 of t. So what do we need to do now? Okay, S31 is just 0. Maybe I do this in red, yeah? So this is just S31 times psi1 of t, yeah? Maybe, yeah, I do this in a different color, in green also, yeah, that you can see this. Yeah, S32 times psi2 of t, okay? This is known, so here it's green. So now we draw this component, and this component looks like this. In this example, of course. Yeah? So this is S32 times C2 of t. And the difference, again, is our missed basis function. So we see, okay, here, this is the difference, yeah, and this is SD of t. And of course, this is not complicated if we now want to map this signal, yeah, into a basis function, we only need to ensure, yeah, a unit energy. This means the shape is known. This is t. Yeah, I draw it here. This is the shape. Yeah, and now we normalize this corresponding to unit vectors in a traditional vector space. S23. 3. Yeah, this is everything is S23. This is everything is S3. Yeah. 2, 3. My mistake. Okay, S23 is of course 0. We don't need the third basis function in order to represent S2 of t. Yeah, and then again we have here this weighting t by 3 by t, because the width here is t by 3. So, and now we basically have everything. So we could say we have our basis functions, and we don't need more basis functions, because the fourth signal can be represented by S1, by psi1, psi2, and psi3. You can immediately see this. We don't need a further basis function, and we want to ensure a minimum dimension of the signal space. So this means step 4, yeah, is just to say step 4, S4 of t is equal to S41 times psi1 of t. It's known. Of course, this needs to be calculated. Yeah, and you can immediately see in this example, this is again u naught times 3 by 2 plus S4 2 times psi2 of t plus S4 3 times psi3 of t. Yeah, and all the coefficients are the same, and we don't need a further basis function. Maybe you write this. A further psi4 of t is not required. So, and now we can say we have the basis functions, 3 basis functions, and we have the signal vectors now. We could say the signal vectors are the following vectors. We could say S1, the signal was only built by means of the first basis function. So always, if you use Kram-Schmidt, you always have only a first component here. So it's in our case, u naught times t by 3, right? So this was the first component here. S11 is u naught times square root of t by 3. And this is shown here. We don't need the other basis functions. Then S2 in our example was just this, u naught times this, u naught times this, and 0. So we don't need the third basis function to represent the second signal. Of course, the third basis function, this one, yeah, and the second signal are orthogonal because the third basis function is just at this position. So, and then S3. So how does it look like? S3 is, of course, 0 u naught times square root of t by 3. In this example, u naught times t by 3. And the last signal, yeah, is u naught times t by 3, u naught times square root of t by 3, and again u naught times square root of t by 3. That's all. And now we have the signal vectors. So 4 signal vectors. Yeah. In order to draw now the signal space diagram, this is a little bit complicated, and in the exam for sure, our signal space diagram is not three-dimensional. If there is a task corresponding to this topic, of course there is, yeah, the signal space will only be two-dimensional, yeah, because in 3 dimensions it's always a little bit difficult to draw this, yeah. Now it depends. I just have done it like this, yeah. Say it's this, yeah. Maybe draw this. Maybe here in this direction, this is psi1 of t. All the components are positive. This is at least an advantage, yeah. So this is the first basis function. Let's say draw. This is the second basis function in this direction, yeah. Oh, here, okay. And then draw, and then in 45 degrees. Oh, this was not good. Draw, let's say I start here, and then 45 degrees should be here. Yeah, this is basically C3 of t. Maybe I shorten this. It's this, yeah. So this is, let's say, C1 of t. No, draw. So this is C1 of t. Let's say this is C2 of t. Let's say this is C3 of t. And now we can represent the signals in this signal space. Again, I could say I define just an abbreviation. A is equal to u naught times square root of t by 3. Okay? And you see, this is a square root of an energy. Why? Square root of an energy. Why is this a square root of an energy? The answer is very simple, because the sum of the coefficient squares is just the energy of the signal. So this means these vector components, if you take a look at the unit, they are always square roots of energies. And the first signal, of course, has an energy of u naught squared times t by 3. And you see, here, if you take a look at the signal vector, this to the square is u naught squared times t by 3. So now we can say, okay, let's say for 5 units to this direction, and again 5, let's say this is A, yeah, and then I say for 5 this is A, and then for this is this is A, and this is A by 2, yeah, this is A, and then in this direction I say this is, let's say, and this would be nearly 2. Here, this would be A by 2, and this would be A, yeah, in this direction. So, and now how could we draw this? S1, how does it look like? S1 is co-aligned, yeah, with our first basis function because it only depends on the first basis function. This is S1. And you will always get these results if you use this Kahm-Schmidt orthogonalization procedure, yeah. So, and S2, for S2, we only need the first and the second basis function. If you use this procedure, or even only the first basis function for special examples. Yeah. Now, let's say this one, yeah. So we have A and A, so A. So in this points, unfortunately, exactly, yeah, because I don't have 3 dimensions on this tablet, yeah, exactly in this direction, yeah, and you cannot see a difference between C3 of t and which points basically orthogonal to this area here, yeah, of this tablet, yeah, but this would be just, yeah, the front plane. So this would be S2. Yeah. And then we could say, okay, how can we obtain S3? And for S3, we have no component with respect to the first basis function. Yeah. We have this component with respect to the second basis function and this with respect to the third basis function. So we could do it like this, let's say. If I do it in green, yeah, you could say, okay, if I want to go in this direction, I could say, yeah, this, yeah, this would be again a plane, yeah, and we would have A with respect to C3 of t and A with respect to C2 of t. And then this vector here, yeah, this would be S3. Yeah? And then there is, of course, a last vector, and this last vector is the longest vector. Yeah? And this vector is basically S3, S4, and it has all components. So we could say, yeah, how does it look like, this S4? It looks like this. So we could say, let's say I draw this in draw orange also, I do this approach. Yeah. So this, yeah, and then say 3, 5, 3, 5, yeah. This is the endpoint of this vector. Again, you don't see a difference, yeah, in the directions of S2 and S4 because this drawing is 2-dimensional, yeah, but it's basically here, yeah, it's this vector. Yeah, I hope you can see this. It's basically here, if you assume that we have a cube here, yeah, then it's this vector. So this would be S4. Yeah, in MATLAB, if you draw, let's say, 3-dimensional diagrams in MATLAB or Octave, you can usually rotate your diagram and then you can see, okay, S2 points really in a different direction than S4, of course. Yeah, but this would be the signal space diagram in this example. So, and now let's say we proceed, yeah, with another task, and this task is quite important because we take a look at sinusoidal signals. So, and this is 5 2, okay? And then you can see, consider the following 8 signals. So we have 8 signals. But for these 8 signals, you see that S5 of t is equal to minus S1 of t. So there's nothing new in S5. Yeah? S6 of t is minus S2 of t. So we know the signal vectors need to be antipolar, yeah, because we have this notation here of the signals. S7, so we have 8 signals, and this is minus S3 of t, and the 8th signal of t is just minus S4 of t. So once we found the signal vectors for S1, S2, S3, and S4, we also have the signal vectors for S5, 6, 7, and 8. And the signals are given as this. Yeah. Let's say here I assume that it's written like, for instance, S1 of t is equal to, let's say, U naught times cosine of 2 pi fct. Yeah. And we do it like this. 0 for it's U naught times cosine of this for null 0 is larger or equal than t, is larger or equal than capital T. And it's 0 outside this interval. How could we draw this? This is the first signal. So the first signal looks like this. And if C, yeah, this is the center frequency, and here we assume, in this example, it's written, yeah, there is an integer number of cycles within the simple interval. So it's written in the task that Fc is just k times 1 by t. So there is an integer number of cycles within this simple interval. And here I assume k equal to 2, just for this example. So how could we draw this? So we could say the first signal looks like this, S1 of t. Yeah. So we have, let's say, this is one period, this is another period of this cosine, and this is just our interval t. Okay. And now we draw here a cosine wave. So this means if we start, let's say, here, then this point is here. Okay, then we are here again, and here, and here. So it looks like this, right? So it's a rectangular shaped cosine. So in here, the amplitude is U naught, okay? The second signal is just a shifted version of this signal, okay? So we say S2 of t is equal to, let's say we write this like this, U naught cosine of 2 pi fct plus pi by 4. Again, in this interval, in this interval, yeah, and 0 else. But it's interesting to note, now I just write the third signal, and the third signal is just this one. It's U naught times cosine of 2 pi fct minus pi by 2, 0 else. Okay. And we want to find or to determine the dimension of the signal space of S4, yeah, let's say of t is equal to minus, plus 3 by 4 pi. This is the only difference, okay? I just show there's the phase 3 pi by 4. And now determine the minimum dimension of the signal space, A. Maybe you require Gram-Schmidt, but we don't need this because take a look at part B and then you see there is an addition theorem. And the addition theorem is cosine of x plus y is equal of cosine of x times cosine of y minus sine of x times sine of y. Of course, you could use Gram-Schmidt, but it's much simpler. And therefore, in our case, if we want to represent the cosine waves with these different angle or phase shifts here, we could say cosine of 2 pi fct plus a certain phase shift, phi I. let's say this phi corresponds either to pi by 4, pi by 2, 3 by 4 pi, and so on. And this can now be written as cosine of, this is this y, yeah, I just changed the order of phi times cosine of 2 pi fct, okay, and then minus sine of 2 pi fct, and there is a factor before, and this is, of course, sine of phi. Okay, this is valid. And now look at the following integral. You can check this at home. It's quite simple. Integral from 0 to capital T cosine of 2 pi fct times, I know the minus sign is not important, but we just do it here because we want to have it as a part of our second basis function, times sine of 2 pi fct. If this fc is an integer multiple, yeah, if we have an integer multiple of cycles in this integration time, you can use again an addition theorem to show that this is 0. So this means a cosine and a minus sine, which we know from Bend-Pass-Lopez transform or Lopez-Bend-Pass transform, these quadrature carriers, they are orthogonal. So this means the cosine and the minus sine component can be, after a certain rating, used for the basis functions. And of course, we can basically mathematically describe all 8 signals just by a linear combination of a cosine and by a linear combination of a minus sine wave. So this means our dimension of the signal space only needs to be 2, because we already know, yeah, that we can decompose expressions like this into a cosine and the minus sine components, and cosine and sine build an orthogonal pair. So the only thing to do is we need to normalize these basis functions. Yeah. So this means we have the basis functions. So this is B. Yeah. And we only need 2 of these basis functions. And this is the first, this is the first one. Draw this, draw this. This is the first one. Okay. And then we need the second one. Draw this, this. Yeah. And we just define, because we know this from, for instance, Bend-Pass-Lopez transform, yeah, that the second basis function is minus sign. This is just a definition. Yeah. This is not necessarily required, yeah, but it's useful for this definition. So here's t. Let's say this is again one period of this cosine wave, and this is one period of the minus sine wave. Okay, so now we draw the cosine here. This, and this is, of course, our first basis function after a normalization, and then minus sign. This gives our next basis function. So we start here. Yeah, we go to minus, then we go to this, then we go to plus, and then again we are at minus. Yeah, and this gives a minus sign. It's like this. Yeah, and again here, this. Yeah, it's correct. Yeah, this, and this. So 2 periods of a minus sign, 2 periods of a cosine here. Yeah. So, and then we say this should be C1 of t, and this should be C2 of t, just per definition. And the only thing we need to do is we need to know how large is this rating here at these axes. Yeah? And then you say, if you have a periodic cosine, let's say we write this here, periodic cosine, periodic cosine wave. then we say the second moment of this periodic cosine wave is m2, yeah, is equal to, let's say the amplitude is just u naught with amplitude 1, let's say, then the second moment is 1/2. Why? Because the effective value of this cosine is 1 by square root of 2. This means the mean power is 1 by 2 if the amplitude is 1. If we now integrate over the time, we would get an energy of 1/2 times t, but we want to have an energy of 1. So this means we need to weight here by 2 of t, because if I square this value, I get 2 by t, yeah? And the mean power of this would be 1 by t, system theoretic power, integrated over the time gives 1. So this means here again, we have this weighting of square root of 2 by t. So both the cosine and the sine need this weighting. And the rest is quite simple, yeah, because we only need, you can use the, you can obtain the coefficients, of course, by these inner products, yeah, but you can simply use this addition theorem to obtain all the vector components, yeah. So now we have the orthogonal basis functions, and we don't need more. We can use both basis functions, which are orthogonal, and the linear combination of these, yeah, is just our signal. So we can see what we see here, this one, is basically psi1 of t, yeah, for, let's say, in this interval. This is psi1 of t, but weighted, yeah, this is psi1 of t. And if we weight psi1 of t, yeah, with square root of t by 2, then it's exactly a cosine. And this minus sign, this is a weighted version of the second basis function. And therefore, we can say in C, we can easily obtain the signal vectors. And this is so important because the modulation schemes used for bandpass transmission, for radio channels, need to be such bandpass signals. Yeah? So the spectrum centroid is not at 0, it's at, let's say, FC. So the first signal only has a first component, of course, because the first signal is just the cosine. This is the first signal. How do we have to weight this cosine in order to obtain the signal? We have to weight this, because there is no second basis function. We don't need to calculate anything. We just have to think about the fact, how do we have to weight this signal in order to obtain the first signal? Yeah, there is no sine component in the first signal in this one. And now we can proceed and can say, okay, let's say we go to S3 for the first. S3 is a minus sign. Now look, S3 is cosine of 2 pi fct plus pi by 3. And if you take a look at this, what happens if this is a cosine? If this is a cosine, okay, it is a cosine wave. And if I shift this cosine wave by pi by 2, yeah, then I need to shift this. So this is 2 pi, this is pi, and this is pi by 2. And if I shift this by pi by 2 to the left, then I get this, right? This, and then this. Yeah. And then if I shift this, we see this is minus sine is equal to cosine, yeah, plus pi by 2. So this means the third signal, yeah, the third signal is exactly, yeah, can be exactly built by means of the second basis function. We don't need more. So it's 0. And then this component is again u naught times t by 2. Yeah, this is the third signal. And of course, we already know that S5 is just S1 with a minus sign. And the question is, what is, for instance, S2, the signal vector S2? And this can also easily be obtained because here we have the addition theorem required. And we basically only need to calculate this cosine of phi e and this sine of phi e. Now let's say for S2, the phi 2 is just pi by 4, right? And then we say cosine of pi by 4, what is it? If we have a cosine wave, this is 1 by square root of 2. And sine of pi by 4, what is it? Yeah, because this is the addition theorem we require. What is it? A sine wave is also 1 by square root of 2. So this means we can write here 1 by square root of 2 times u naught times, and now we have to think, this is not the basis function. This is the basis function times square root of t by 2. So this means times square root of t by 2. This gives exactly our required component. And here again, the same. So this is this one. So, and then we can check the energies. The energy of E1 is just u naught squared times t by 2. Okay. The energy of E3 is, of course, u naught squared times t by 2, because the mean power is u naught squared by 2 times t is the energy. And now look if this is correct for E2, because E2 has the same energy. It only differs in a phase shift from S1, or S2, sorry. Now let's calculate this. If we write this a little bit different first, we could say this is the same as if I put this square root of 2 within this square root, what do I get? Or is it required? No, it's not required. It's nice as it is. So then we could see E2 is equal to, if I square this, I get 1/2 times u naught squared times 2 by this, 2 by t by 2. And then the same again, plus, this was the first component, let's say, the energy of the first component, and then plus 1/2, so this value, squared, times u naught squared times t by 2. And we again get u naught squared times t by 2. And you see the energy is correct. So at least the energy, so the magnitude here is correct, but even the sign is correct. So, and then if we take a look at S4, we need to calculate cosine of here 3 by 4 pi. So where is 3 by 4 pi? So this would be here, right? So this is pi, and 3 by 4 pi would be here. So it's negative. So this means this value is minus 1 by square root of 2 u naught times square root of 2 by t. And the next component, sine of this, I just have to draw it. This is a sine. Here is pi. So this is also negative, minus 1 by square root of 2 u naught times square root of t by 2. So, and now we have all the signal vectors. And we can draw the signal space diagrams. And we immediately see, of course, that all the signals, and then we can stop, that all the signals have the same energy because they have the same amplitudes. And this is a well-known signal space diagram because it's the signal space diagram of phase shift keying. We can encode our information to be transmitted. We have 8 signals. We can transmit 3 bits with 8 signals, basically. And we can encode the information by a change of the phase of a cosine carrier or sine carrier. So let's say this is our spacing. This is again our spacing. And we define again, just for this drawing, A is equal to u naught times square root of t by 2. Okay. Then we start with the first signal vector. So this is A, this is A, this is minus A, and this is minus A. So we start with the first signal vector. The first signal vector just points in this direction. So we only have this. And it has a length A or an energy u0 squared times t by 2. So this is S1. So where is S2? This is the second basis function, or let's say S3, and S3 is exactly here because S3 is orthogonal to S1. So S5 is just minus S1. It's written here. S5 is minus S1. So we can say, okay, this is just S5. And this is, of course, just S7. This is minus S3. And the remaining signal vectors have the same length because they have the same energy. Yeah, we could say, okay, they have an amplitude parameter, which is A divided by square root of 2. Yeah, and in order to draw this, I could say they all have the same energy. This means they have the same length. Yeah, and they are located here. They just differ by means of the phase. Yeah, and then we could say S2 is just this and this. So it just points in this direction. This is S2. And then we say, okay, what is with S4? And S4 has two negative, oh, then there is a mistake in my thinking. Cosine of, wait, 3 by 4 cosine. 3 by 4 pi. Where is it? 3 by 4 pi. Oh, it's cosine of 3 by 4 pi. This is negative. Yeah, this is correct. The first component is correct. Now let's take a look at the second component. Maybe I was wrong. So a sine, this is a sine, right? So here is pi, and this is pi by 2. And then we have to take a look by 2. Yeah, and then we have to take a look here, 3 by 4 pi, right? So, and then it's positive. It's positive. This component is positive. So it looks like this. So this is S4, so I had a mistake. Yeah, and of course the other are just antipodal. So this is the last one, this is S8, and this one is S6. Yeah, and this is the signal space diagram. Yeah, and we could calculate now the Euclidean distances, but we don't do it today because we are late. Yeah, but this is the signal space diagram, and be aware this angle here, and then we really stop. This angle, if we want to calculate this angle is pi by 4. So this is the spacing, yeah, between the signal vectors, this angle. And this is just our phase shift, if we interpret this as phase shifting. So all signals, yeah, differ in a phase by at least pi by 4. And there is an equal spacing in this phase. So it's the signal space. This is, of course, this is the next topic, modulation schemes, but this is the signal space of 8 phase shifting. So a modulation scheme where we shift the phase depending on the symbols to be transmitted. Yeah. And we have 8 different levels for this phase. Of course, E, yeah, the signal energies are all the same. IE is equal to u0 squared times t by 2 for all I. And then we stop. That's all. Thank you. And Merry Christmas, of course. Merry Christmas.
Thank you, sir. You too. Happy New Year and Merry Christmas.
Thank you. Ich krieg da echt, ich weiß, ich habe mit dem Zinsinger gesprochen und gesagt, da ist noch so viel Zeit. Ich weiß nicht, wann das losgeht.